Okay, welcome to topic 13, data representation. So this video is going to be split into three parts. The first part is going to cover section 1 of topic 13, which is user-defined data types. Then we're going to move on to section 2, which is file organization and access. And finally, we'll finish with section 3, which focuses on floating point numbers. Now, the material that we're going to address in this video encompasses about 15 to 20 points worth of questions on paper 3. So pay attention, it's an important topic. Now let's start by taking a look at topic 1, which is user-defined data types. This is an extension of the previous programming concepts that you've had to learn for topics 1 through 12, so paper 1 and 2. Here we're going to cover non-composite data types, composite data types, and classes. Now, non-composite data types are defined as data types that don't refer to other data types. So a great example are primitives like integers, characters, etc. But also some data types we're going to look at here. Specifically primitive, enumerated, well, we've already talked about primitive, but enumerated and pointer data types. These are used to refer to a single value at any given time that cannot be broken down into smaller components. So just a single value. And these are all examples of non-composite data types. This is the one that you probably recognize the most easily. It's an integer, and the value of the integer is 23, and this can't be broken down into any other types of data. This right here we'll look at more closely in a second. Now the first type of non-composite data type, as we went over, is going to be the enumerated data type. And this is weird because it doesn't actually refer to a specific type of data. It's more just like a list of values. And these aren't necessarily even strings. So here's a typical example of enumerated data type. We're starting with type. We have the name of the data type, which is going to always start with T, so T colors. And there are only 3 specific values in this data type, and that's red, blue, or green. So what we're going to do, so we created this data type, then we can actually declare a variable that has this data type. So that variable is called dcolor, and it's of data type tcolors. And what this basically means is that tcolor can only be one of these 3 values. So we can only assign red, blue, or green to dcolor, which is what we do right here. Dcolor is blue. Now, what we can do is we can actually use addition to access other values, other data types. So for example, right here we have dcolor is blue, but if we wanted to assign green to the next color, we would just do dcolor plus 1, and that would give us green. But again, these aren't strings. It's just kind of like a list of what we would call really atomic values. And they just store a limited list of values. And really, they are used to denote and allow us to access a specific list of values that apply to some specific scenario. We're rarely going to do any complex operations with these. So look at an example of enumerated data type on the A-level exam. Right here it says write pseudocode statement to define the data type Q1 to hold the names of the first 3 months of a year. And obviously these are all the months in a year. So we're going to call this data type Q1. So in order to write the pseudocode, we're just going to do type Q1, and we're going to do equals to parentheses the first 3 months, so January, February, and March. So to kind of go over some of the syntax, type, name of the data type, and then parentheses, which is also what we saw right here. We saw type, name of the data type, and then parentheses. And all we need to do here is just define the data type. So if we go right here, we can see that we got the correct answer. And that's a very typical enumerated data type question that you might have. Now to look at another question, it says define using pseudocode the following enumerated data types. School day to hold data about the days students are usually in school, and then weekend to hold data about the days that are not school days. So it actually doesn't give us that much information, but basically we want to have type, school day. And then we can kind of just imagine, we can just say that we'll have equals, and then we can kind of just say that we're gonna have Monday. So just to highlight, we have type, we have the name of our data type, parenthesis, an equal sign, parentheses, and then we have each value that's going to be part of our data type separated by a comma. Now next, we can to hold data about the days that are not school days. So again, we're gonna have type, name of our data type, equal sign, and then parentheses, and this is probably just gonna be Saturday and Sunday. Let's go check the mark scheme, and yeah, that's the answer. So really what you just need to remember is the syntax, but these are pretty straightforward questions. Now let's take a look at a data type that is slightly more complex, which is the pointer data type. Now pointers are something that are more typically used in C++ or C, and really in C. And I don't really even understand why they're included in the A-level curriculum, but here we are. Now rather than referring to a piece of data, they're used to reference a memory location. And by memory location, we mean an address that looks something like this, like a hex address in memory, not C, like D, F, something like that. So they store an address in memory itself rather than the data. So to understand how this works, let's look at an example. Here, we are declaring a typical variable of integer data type age. Then we're going to create a pointer. So actually we're going to create a pointer data type specifically. Not the pointer, but just a pointer data type. So you have type, and we're calling this data type integer pointer. And basically that means that we're going to have a data type and this data type is going to basically allow us to hold an address of an integer. And we signify that by this caret followed by integer. So we have the caret and then the data type. So let's say, for example, we had a data type like, let's say we had, I guess if we had like a string, for example, right? Then we would just have caret and then string. So we're just creating the pointer data type, and now we're going to create the actual pointer right here. Declare age pointer of type integer pointer. So we're creating the variable, really we're creating the variable age pointer. It's a pointer variable, and it's going to be of type integer pointer, which means that it's going to be the address in memory of an integer. And to actually store, and basically to store the address of age right here, to store this address right here, we're going to do this. We're going to do age pointer is equal to caret again, and then the name of the variable. So this caret notation is very important. And then now, let's say that we want to actually get the data that is at that address. So we want to use this address that's stored at age pointer to get the data located at that address. So you want to get the data that's stored at the address of age pointer. So let's say the address of age pointer is like at 9E CD. Let's say that's the address that's stored in age pointer. And there is some data, let's say the data is going to be 59 that's stored at that address. So if you actually want to get that 59 and store it in a variable called new age, which should actually be an integer, we would take age pointer. So we do use age pointer, and then we put a caret afterwards. Before we had a caret in the beginning of the variable that we were working with, the data type or the variable. Here we'd have the caret afterwards, and that means that new age would then just be equal to 59. And that's basically how the pointer data type works. Here's another example. So right here, this is a more complex example. We've created a data type, tcolors. This is an enumerated data type, right? And we've created a variable of type tcolors, the color, and we stored the value blue. So the color is equal to blue. But now we're going to create a pointer data type that only allows us to store addresses of tcolors variables, of variables of the tcolors data type. So right here, we can only have addresses of variables of the tcolor data type. So we have our caret followed by the name of the data type. So then we're creating a pointer right here of tcolor pointer data type. So that means that in my color pointer, we can only hold addresses of a variable. We can only hold addresses that refer to something of the tcolor data type. And here, we're going to take the address of this dcolor, and we're going to store it in my color pointer. So now my color pointer is like at 79EFG, and this is going to, if we access, and this address is corresponding to blue. But here we created another variable called new color, and this should be probably of tcolor's data type. And we want to make new color equal to blue. And actually right here, we had age pointer. So actually this is a mistake. We're not going to do dcolor. We're going to do my color pointer. So this is wrong. We're going to do my color pointer and then caret. And that's going to make new color equal to blue. So it's a slightly more complex example of how pointer data types work. So now let's go ahead and let's look at an example. So it says right here, 2 descriptions of user-defined data types are given. Give appropriate type declaration statements for each. So a data type is used to hold a set of prime numbers below 20. These prime numbers are this. So this is going to be an example of enumerated data type because we just want to hold a list of some values. So we can just do type prime, actually this has got to be capitalized. We can do type prime equals 2, 3, 5, 7, 11, 13, 17, and 19. Now we want a data type to point to a day in the week, for example, Monday. So I'm actually not going to look at the mark scheme, but probably what I would do is I would create a data type, like I would do type days equals, let's say, I'm just going to go ahead and write this out. Then what I would do is I would create a type. If you go back to our syntax right here, we're going to create a type days pointer, and that's just going to be equal to, let's just make sure we're using the equal sign. It's going to be equal to a caret and then days. And let's go ahead and look at the mark scheme. Okay, so right here we have, so this one is obviously correct, and here we have a few different answers, but type tday pointer equals day of the week is totally valid. And those are some good examples of enumerated, of how to use enumerated and pointer data types. Now let's look at another similar example. So right here it says write pseudocode to create an enumerated type parts called parts, which includes all of these. Just to make our life easier, I'm just going to do type parts equals, and then I'll just put some parentheses, and that's it. Now write pseudocode to create a pointer type called select parts that will reference the memory location in which the current part name is stored. So what I'm going to do in this case is I'm just going to say type parts pointer is equal to caret and parts. Let's go. Yeah. Actually, I guess I should have called this select parts. My bad. Select parts. So type select parts. But everything else is correct. So that kind of wraps up non-composite data types. Let's move on to composite data types. So in contrast to non-composite data types, these can have variables, or these can have other data types in their type definition. So this is a data type that can have multiple other data types as part of itself. Now, some examples of composite data types are going to be records, sets, and classes and objects. Records are going to be the most prevalent on paper 3 of the exam. Sets are something that's like mentioned, but I've never seen any evidence of it on the exam. And classes and objects are something we're going to go through, but this is not going to be a full description of object-oriented programming. So start with records. Basically, right here is an example of a record. So here we have a type. The name of the data type is student. It's a student data type. But any student, any student record will have 4 pieces of data: a string for name, a string for ID, a string for birth date, and then a real variable for GPA. So we can create a student variable like this. So we have student1, which is a student data type. And so that's how we create the variable. But then if you actually want to assign some data to that record, then we can basically access each individual part of that record separately and assign it some value. Equally, we can also, while we can declare a single variable as a record, we can also create an array of records. So this is an array of 30 student records. So it's difficult to think of like a good analog because like normally this is to do something like this, I would use object-oriented programming. I guess maybe a map, if you're familiar with that data structure, would be similar. But essentially, we're creating a data type that allows us to store multiple pieces of data of different data types. We're going to start with the type definition with the keyword type. We'll have our declarations inside, and then we end our definition with this end type. So let's go ahead and look at some examples. Right here it says define using pseudocode the composite data type club meet. This will hold data about club members that includes first name and last name, the 2 days they attend, one on a school day and one not on a school day. And it says use the enumerated types you created in part B. So those 2 enumerated types are going to be school day and weekend. And remember from our previous example, these would include, so school day is going to be something like this. So it includes Monday through Friday. It's an enumerated data type, and weekend is going to be Saturday and Sunday. But these are going to be the data types. So if you want to create this declaration, we can just do type. We can start with type, and then this data type is going to be called club meet. And then we can declare first name, which is just going to be a string. We can declare last name, which is also be a string. And then, okay, it's the 2 days they attend, one on a school day and one not on a school day. So I guess we can just create a variable called day 1, which is just going to be of school day data type. And then day 2, which is going to be of weekday data type, or weekend data type. So we'll call this day 2, and that's going to be a weekend data type. And then end type, and that's pretty much it. So let's see whether this looks the way it's supposed to. And yeah, it pretty much does. You got strings for these, end type, type definition, and that's our first example. Now let's look at another one. Here it says data types can be defined using pseudocode. And we have a data type here called building record. And we have this building record data type right here. So right here it says a variable building register is declared in pseudocode like so. So we have a variable building register of building record data type. So our task is to write pseudocode assignments to assign 1067 to the building ID of building register and house to the building group of building register. So we specifically want to assign a value to this variable in the building record and also to this variable. So what we can do is we can take the name of our variable and we can say building register dot building ID dot being used to access an individual record is going to be equal to 1067, and building register again dot building group is going to be equal to house. And that's pretty much it. I guess I forgot the quotes. This is a string, so it should be quotes. And we'll take a look at one last problem. Well, this is actually part of the same problem we just looked at. It says the type definition for building record is changed. The data type for building group is changed to an enumerated type, building type, with the values of house, bungalow, apartment, and farm. Write the type declaration for building type in pseudocode. So building type is going to be an enumerated data type. This is just a great way to review. So we can have type and building type, that's going to be equal to house. It says write the new declaration for building group in pseudocode. So if you actually go back right here, this is building group, and we have a new data type. So we have a new data type called building type, so which is right here. So if we basically wanted to just change that, then we would be changing this to the declare building group, and then our new data type would just be building type, which is what we specified right here, this data type. And now it says write the new pseudocode statement to assign house to building group of building register. So we just have building register dot building group, and to that we're going to assign either house, bundle, or apartment without quotes. So we'll just make it house, and that's pretty much it. Now for our last example, it says the composite data type pet is used to store data but various pets of a group of students. Write the pseudocode statement to set up a variable for one record of the composite data type. So if we wanted to just set up a variable just for one record, then we might just say declare new pet, and then that's going to be a pet data type, and that's it. Write pseudocode to store details of the following pet in the variable that you set up. So we had a variable called new pet, so we could do new pet dot pet name is going to be Tibbles. This doesn't have any quotes, so I assume it's just going to be a probably just an enumerated variable, or maybe, I don't know, it seems like this should be a string actually. We don't really have any specific definition, or actually do we? Yeah, we do have strings, so these are strings. This is a character, and this is a string. So new pet dot animal type is going to be equal to cat. We have new pet dot pet age is equal to 8. New pet dot pet gender is going to be M. We're just using a single quote for character. And then new pet dot owner name is just going to be a string Jasmine Smith. And that's pretty much it. And yeah, I think we're good to go. We had a different variable name, but it doesn't really matter. So that about covers it for records. Now let's take a look at sets. So sets, again, are very rarely used. So basically, it's an unordered list of values of a certain data type. And also, every value in a set is going to be unique. So we're not really going to have any repeats. And this is how you define a set. Basically, say type, you have your variable name right here, and then you say set of integer. Now, in terms of actually defining a variable, you can actually set the values that are going to be in that set in the variable definition. The idea is that these are used in intersection, union, so kind of not exactly Boolean operations, but if we're trying to, for example, figure out between two sets what they have in common or put them together, that would be a use case, but I haven't really seen this on the A-level exam. So I'm just going to show you what this is, and I'm not really going to go into too much detail in it. Now next we do have classes and objects. So again, classes and objects, I don't want to go into too much depth because object-oriented programming is a whole section on this exam. But this is basically an example of a class. We have a private class variable, a public serial number, we have our constructor right here, and then we have a public method on the class. And we're just going to do a practice problem just to show how we would solve a problem like this in this context. So right here it says the program is to be rewritten using object-oriented programming. So that's our building record example we looked at before. The data type building record is to be changed to a class, building class. The properties for building class or building ID, building group, owner name, so you've got all of these right here. All properties are to be set to private, and we're just going to solve this problem right here. Write the declaration pseudocode for owner name as private. So we're just going to have private, remember that's a private access modifier, owner name, and then I guess that would be a string. And that's it. Explain why the properties have been set to private. So ensure attributes can be accessed only by the class's own methods. So this is if we don't want to be able to access variables or attributes outside of a class. So I'm not going to go into any more depth into object-oriented programming in this context because this is covered in full in another topic for which I'm going to make a video, topic 20. So that being said, let's move on. Okay, now let's take a look at part 2 of topic 13, file organization and access. In this section, we're going to talk about how data or records are stored in files. So for example, if we have a .txt file, we're going to talk about how individual records, which may be letters or other pieces of data, are stored in that file. So first we'll talk about how they're organized in that file, looking at 3 different methods. Then we'll talk about how we can access individual records in a file from something called a key. And we'll look at 2 methods for doing that, sequential and direct file access. Finally, we'll talk about a method of accessing files called hashing, which is used both in direct file access and in random file organization. Let's get started. Now, the first type of file organization that we're going to talk about is going to be serial file organization. Now, with serial file organization, basically records are added to a file in the order in which they're added, or they're stored in a file in the order in which they're added. So for example, if we think of every record in a file being stored at a particular position, so 0, 1, 2, 3, 4, if we add the record A first, that's going to be stored at position 0. If we add the record B second, that would be stored at 1, C, and then D. Now, if we want to find a specific record, we need to do a linear search, so we need to go through every position in our file until we find the record that we want. Or optionally, if we just want to access a record at a specific position, still we'd have to do a linear search, go through every single position until we get the position that we want. Now, if we want to edit a file that employs serial file organization, all we would need to do is we can just directly edit this file. So if you have a .txt file and it uses serial file organization, then we can go in and, for example, we could just go ahead and we could delete a particular record, or we could edit a particular record just by editing that file. This stands in contrast to sequential file organization, where we need to create a new file to update a file. So in serial file organization, records are stored in the order of the key of a particular record. So if you think of pieces of data having keys, so for example, let's say we have A, L, M, J, and all of these are just records. Each of these may have a key. So the key for L might be 1, the key for A might be 2, for J it might be 3, and for M it might be 4. Now when we put this in a file, that particular record is going to go where it belongs according to its key. So if our keys are all integers, then basically in our file, we're going to have all of our data organized in numerical order, in ascending or descending order based on the key. So at position 1, we would have L, at position 2, we would have A, at position 3, we would have J, and so forth. So when we edit this file, we basically need to actually move every record that's not where it belongs, so that we can put in our new record in the correct position according to its index. And this is why we actually do need to create a new version of the file in order to be able to update it, because of the extent of the change that we're making. Now, similarly to serial file organization, records can be found by searching through the file one by one. So let's say we want to find a file at position 2, we would just go through one by one. Or if we wanted to find a particular record, we wanted to find A, we would do the same thing. We'd go through one by one using the linear search method until we found our record. Now the final method of random file organization that the final method of file organization that we're going to talk about is going to be random file organization. But it's not really so random. It employs something called a hashing algorithm that basically decides at what position we're going to put a file based on its key. So if you look at our previous example, we have like A, L, M, and K. And L has key 1, A has key 2, M has key 3, and K has key 4. Basically, we would take this key and we would put it into a hashing algorithm. And that hashing algorithm would tell us what position in the file that record is going to go at. So maybe that hashing algorithm outputs K3. That means that we would store it at position K3 in a given file. This may seem random, but it is determined by an algorithm. But the point of random file organization is that we are basically figuring out where to put records based on the input of a key into an algorithm. And similar to serial file organization, we can directly edit files that employ random file organization. Now let's take a look at two methods of file access. We touched on this when talking about file organization, but if to access a file, we need to go through every record from beginning to end using the linear search method. That's referred to as sequential access. If we're going to access or find the position of a record using a hash algorithm, that's direct access because we can go through without accessing any other record in a file. We'll know exactly what the position is based on our hash algorithm. Versus with sequential access, we're going to have to look through every single record until we find what we want. Now, when we're talking about hashing algorithms, we need to consider the problem of collision. So sometimes when we employ hashing algorithms, they produce the same position given different keys. So going back to our ALKM example, let's say this has index 1, index 2, index 3, and index 4. Now we put these into a hashing function, and what might happen is we put in 2, and we end up with 1. But we put in 3, and we also end up with 1. So both of them lead us to the same position in a file. That's an example of collision. We're putting the keys into our hash function and end up with the same position. Similarly, right here, we've got 5 pieces or 5 strings. We can give these keys of 1, 2, 3, 4, 5. Now in this example, we might be putting in the key for Michael and the key for Toby. But the hash algorithm produces a position of 2 for both of them. Now this is an example of collision, and we're going to learn about 2 types of collision, which are open hashing and closed hashing. Now, again, to describe collision, right here in this example, we have a key of 10 and a key of 15. When you put these into our hash function, into basically where we have our hash algorithm, we are producing an output of 0 and 0 for both inputs, which means that basically this algorithm wants us to store the data of both keys at position 0 in our file. Again, this is an example of collision. Where are we supposed to put this data? Now the first method is open hashing. And open hashing involves storing data in linked lists at every single position in a file. So here we have position 0 through 6, and 5 and 6 are free as well as 3. But at every position in which there is a record, there is a linked list. So let's say, for example, we have keys 36 and 64. So we put 36 and 64 into a hashing algorithm. Put it into our hashing algorithm. Now that ends up giving us an output of 1. But we go to 1 and we already have a record there. So we're going to add the data that corresponds to both keys, 36 and 64. This blue can represent our data. We're going to store those. We're going to add those to a linked list that's located at position 1. And that's how we can that's how we can store data when there's a case of collision. Now, if we want to find a piece of data, so let's say we want to go ahead and we put in a key of 36 because we want to access the data that corresponds to the key 36. Then we would go to position 1 and we would search through our linked list using a linear search until we find key 36 and the data corresponding to key 36. And that's our retrieval. Now, the next method we're going to look at is going to be closed hashing. Now, closed hashing works a little bit differently because if you actually go back to our previous diagram, with closed hashing, we'd have an extra area called an overflow area where we could store data. So for example, let's say we have 36 and we have 64, right? Now, if let's say that we produce the position 0 at 36, and we'll call this 0 right here, right? So that goes to our hash algorithm and we produce 0. So then we could just store 36 right here. But let's say 64 also produces 0. So it goes to our hash algorithm and we also get 0. That means that 64, that key and index, is instead going to go to our overflow area. So we'll have 64 and then whatever data is represented. Now, if we want to find 64, we're going to go through our entire, so we're going to go through basically our primary area. So we'd go through all of these positions, 0 through 6. And if we can't find, so if, for example, we try to find, we get to 0, and we see that only the key 36 is there, then we would just move on and we'd look in our overflow area for our record. So if the hash algorithm produces an index, and the data index does not match the key, so the data at that index does not match, or the data at that position doesn't match whatever we put in, for example, 64, then we would just go look for that data that matches the key in our overflow area. So this is just an area when we have collision, whenever we have a key that produces a position that's already taken, we're just going to put the corresponding data in our overflow area, and that is closed hashing. Now to finish off, let's take a look at a more quantitative question involving hashing algorithms. So right here it says a hashing algorithm is used to calculate storage locations for records in a random access file. Calculates hash values by using the function modulus 3, so mod 3. The function modulus gives the remainder after integer division, which is something you should already know. So for example, if we have 1030 mod 3, that's going to give us 1. Because if we divide 3 by 1030, let's go and do this long division, we would get 3, 9, 1, 13, and we get 4, 12, 0, 1, 10, and then we do 3, and then we have a remainder of 1. So that means 1 is going to be our answer. So complete the table to show the remaining hash values. So in order to calculate the hash value of 1050, we would just do similar long division. 3 divided by 1050, so 3, 9, 1, 15, and then 5, 15, minus 0. And then we'd have 0 again, and so we would just do 0. So actually our hash value is going to be 0 right here. And then if we did 1025, 3 divided by 1025, so 3, 9, 0, 1, we have 2, that's 4, 12, so we're going to have 0 and then 5, and then that's going to be 1. And so 5 minus 3 is going to be 2. So we're going to have a remainder of 2, so our hash value is going to be 2. And this is a question that's connected to the topic we just went over, but it's slightly different, and therefore I wanted to go over it. It also gives us a good illustration, or a really simple example of what a hashing algorithm would look like. So that being said, let's move on to our next section. So now let's take a look at part 3 of topic 13, which focuses on floating point numbers. Now the term floating point numbers is really a short form for binary floating point number representation, which we're going to learn more about. After that, we're going to talk about what normalization is and how this applies to floating point numbers. And then we're going to move on to conversions. So Denary to floating point, negative and positive floating point Denary, and binary to floating point. We'll finish off by talking about the concepts of overflow and underflow, which are kind of key to understanding the interaction between hardware and these numbers themselves. So what is binary floating point number representation, or what are floating point numbers? So these are a format of binary numbers that are used to represent a much wider range of values than is possible with just unsigned binary numbers. Using floating point numbers, we can represent both fractions and negative numbers. Now, because of the capability of this format, this is the industry standard for doing floating point computation in computer programs. So anytime we're working with decimals or negative numbers, or those numbers that are defined to have a floating point data type in computer programs, we're using binary floating point number representation. Now, in terms of their use case, beyond just being used to represent fractions and negative numbers, they are often more efficient for complex calculations, such as those that can be found in scientific, engineering, and 3D graphics related implementations or situations. So now that we know what the advantages are and why we're doing this, let's go ahead and see what floating point numbers actually are. So here I've got two decimal numbers and their floating point equivalents. These are obviously our denary or decimal numbers, which we're used to seeing. And on the other side right here, we've got our floating point equivalents. And every binary floating point number is going to consist of a mantissa and an exponent. Now, the easiest way to understand what the mantissa and an exponent are and how binary floating point numbers work is to consider that they follow a similar format to scientific notation. So if you think about scientific notation, it looks something like this. We have 5.37 times 10 cubed as an example. Here we've got a number, and this number, so this is going to be 5 plus 3 over 10 plus 7 over 100. And we're multiplying this by 10 to the power of 3 to get our answer. So if you want to think about this in terms of floating point representation, this right here, this number in scientific notation is going to be our mantissa, and this right here would be our exponent. Now, the difference between scientific notation and floating point representation is that scientific notation is inherently in base 10 format. So it's representing a denary number, which is why we're multiplying times 10 to the power of something. But with the mantissa, things are going to look a little bit different. So if we were to take our mantissa and exponent, our first binary floating point number, and write it out in a format, in an equivalent format more similar to scientific notation, it would look something like this. We'd have 1.000110000 times 2 to the power of 0.00011. Now the first value is our mantissa, and the second value is going to be our base to the power of our exponent. Now if we wanted to represent this in denary, so if we wanted to go to this denary value right here, we could start by converting the exponent in binary to denary. So this value, this binary number right here is just equivalent to 3. So that means we'd end up with 1.000110000 times 2 to the power of 3. Now, if you want to deal with the mantissa, we need to take a few things into consideration. Remember how I said that floating point numbers could be used to represent both fractions and negative and positive numbers? Well, in this first mantissa right here, we have 1 as our first digit. So our first digit here and here, or in any floating point number, is going to tell us whether the denary equivalent is going to be negative or positive. If this first digit is 1, that means that we're going to have a negative denary number. If it's 0, that means we're going to have a positive number. Now, these numbers, both of these binary floating point numbers, are normalized. And we can go over what normalization is later, but basically what it means is that we're going to have the first digit, and then we're going to have a decimal point, and then everything after that is going to represent a decimal. But decimals here are going to work a little bit different than we're used to. So if you think about decimals in our usual base 10 notation, this is basically how it works, right? Like if we have 5.37, this is equivalent to basically 10 to the power of 0 times 5. Or let's say we have 25, right? So this is going to be equivalent to 10 to the power of 0, so 5 times 10 to the power of 0, 2 times 10 to the power of 1, So we'd have something like this, 2 times 10 to the power of 1 plus 5 times 10 to the power of 0. And then for our decimals, that'd be plus, this represents 1 over 10 and 1 over 100. So it'd be plus 3 times 1 over 10 plus 7 times 1 over 100. And that's how we really get our value. That's kind of how this whole decimal thing works. Well, if you take this and apply this to binary, it's going to look something like this. So here, our first number is going to be the only number. Because this is normalized, we'll look at non-normalized numbers later, but that's going to be the only number that is on the other side of the decimal point. Everything else is going to be a decimal. So that means this is going to represent 1/2, 1/4, 1/8. Because remember, we're working with base 2, 1/16, 1/32, 1/64, 1/128. So I'll just write that right here, 1/128, 1/256, and 1/512. Now, we only have 1 at certain spots, right? So first, we've got a 1 in the first digit. And that does represent whether it's a positive or negative number, but it's still part of the mantissa. And it's going to be represented like, so this is really 2 to the power of 0. And 1 times 2 to the power of 0 is just going to be 2, or it's going to be 1, actually. So this mantissa is going to represent -1, because this is a negative number. So it's a negative number, and we have 1 on the other side of the decimal point, plus 1/16 plus 1/32. So plus 1/16 plus 1/32 times 2 to the power of 3. And if we work this out, we can get our answer right there. Now, if we go down to our second example, right here, this is actually a positive number. So our first digit's not going to give us anything, but our mantissa is going to look something like this, 0.1000. So we got 5 zeros, 1 0, 1 0 0. Now this number is also normalized. So if we have a negative number that's normalized, then we start with a 1 and we have our decimal, and then otherwise we start with a 0, we have a decimal and then a 1, and then we keep moving on. We'll get into normalization later, but that's why this is the format that we can write it in. This isn't always true, but in these cases it is, because these are both normalized. Now, if we wanted to find the value right here, you can see the exponent is going to be, so it's going to be, it's 2 to the power of 3, or 2 to the power of 2, 2 to the power of 1, 2 to the power of 0. So 4 plus 2 plus 1, it's going to be equal to 7. So if you just kind of look at how our fractions work, right here we've got 1/2, 1 to the 4th, 1 to the 8th, 1 to the 16th, 1 to the 32nd, 1 to the 64th, 1 to the 128th right here. This is going to be 1 to the 512th, and that's pretty much it. So we're really going to have a value that's going to be like 1/2 plus 1 over 128 plus 1 over 512. And we're going to take this whole thing and we're going to multiply it times 2 to the power of 7. Now maybe that seems like it wouldn't give us 65.25, but 2 to the power of 7 is a pretty large number. So odds are, especially since we've already got 1/2 right here, we're going to get, like I could see us getting 65.25. Anyways, we're not adding a negative number because we have a 0 right here and we know we're getting a positive equivalent. So to kind of summarize, you can see how we get our exponent, how we get our decimal, how we can represent our decimal values, and how we can represent whether a value is positive or negative. And we kind of referred to a concept called normalization. So that's the next thing I want to cover with regards to floating point numbers, because that's kind of a topic that comes up when we start to do conversions between both of these. And it also gives us more insight into how this concept works. So let's move on to normalization. So right here in this A-level problem, it says the given binary floating point number is not normalized. Normalize the floating point number, show you're working. So if we go back to our previous example right here, a floating point number is normalized when, if it is negative, it starts like this. And when it is positive, it starts like this. So the first number, both the first number and the second number are actually already normalized, and I intentionally chose such numbers so that I could illustrate this concept. So if we go back to our example right here, let's go ahead and write out this number as is, the non-normalized number. So this is in floating point format, but it is not normalized. So at the moment, it's going to look like this. 0.000, I guess we've got 6 zeros, and then 3 ones, times 2 to the power of 100, 1, 1, 1. Now this starts with a 0, so it's a positive number. Hence, we're going to want our mantissa to look to start like this, 0 and 1. And basically what we need to do is we need to alter our mantissa. So we can't actually change the number itself, but so we're not going to change the entire floating point number. But remember that this is like a floating point number is essentially like scientific notation. So if we have in scientific notation 5.37 times 10 to the power of 20, and we want to make this number right here. So if we want to move the decimal point of this number right here, what that basically means is that we're going to need to make this number right here small, or actually bigger, because this is going from 5.37 to a smaller number. This is going to become 0.537. So then we'd have times 10 to the power of 21. Alternatively, if we had a number like, let's say we had 0.0079 times 10 to the power of 31. And let's say we wanted to turn this into 7.9. So basically what we need to do, we're going to be making this mantissa bigger. We're moving over 3 decimal places, which means we need to actually make this exponent right here smaller. So we end up at 7.900, you could say, or I guess 000, we have 4 decimal points, times, so we have to move it over. So basically we're moving 7 over by 3 decimal places right here. So it's going to be times 10 to the power of 28. Now, this part right here is very similar to what we're going to be doing over here. So basically what we want to do is we want to move this part right here over so that the first one is right here. So in order to accomplish that, we're going to have to move this a certain number of places. So this one is going to have to move over 1, 2, 3, 4, 5, 6 places. So that means that basically we're going to make this number bigger, this mantissa bigger, and subtract 6 from our exponent. Now if you calculate our exponent, let's say this is going to be, it's 2 to the power of 0, 1, 2 to the power of 3, then this is going to be equal to, this is 2 to the power of 3, 2 to the power of 4, and this is going to be 2 to the power of 5. 2 to the power of 5 is 32, so this is going to be 32 plus 4 plus 2 plus 1, which equals 39. So really, we have 0.000000111 times 2 to the power of 39. But we're going to move this over by 6 decimal places. So we're going to make it, so we're going to multiply it by 2, essentially 6 times. So if we do that, we're going to end up with 0.1110. I guess we've got, how many bits do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits. So 0.110, and then we're going to have 5 more zeros after that. So 0, 0, 0, 0, 0 times 2, and we're moving this over about 6 places. So it's going to be 2 to the power of 33. And that means that right here, we're going to have a mantissa that looks like this, and then 0, 0, 0, 0, 0, 0. And then we're going to have an exponent that looks like this. We're going to have 1, 0, 0, 0, 0, 1. Because this is equal to 2 to the power of 5, 2 to the power of 0, and we're going to get 33. And that's how normalization works. We end up with something like this. Let's go check the mark scheme, and it looks like we are correct. Now that being said, let's move on to another normalization example. And I like going with normalization first because again, this gives you a much better understanding how the mantissa and exponent work before we go on to more complex operations. So right here, a binary number is stored in the computer system. We have the mantissa and exponent, and state why the number is not normalized. So just looking at this at a glance, this is going to be a positive number, but for it to be normalized right here, we'd have to start with 0, 1. But instead we have 0, 0. So that's the reason that it's not normalized. So positive, but doesn't start with 0.1. Now if we want to write the normalized floating point representation of the number, we're going to have to go through the same process. So right here we can write this as 0.00111110 times 2 to the power of, so that's 2 to the power of 0, 2 to the power of 1, 3 to the power of 4, so 16, 8. So that means that we're going to have 2 to the power of 24. Now we need to move this 1 over 2 times, which means that our mantissa is going to look like this. It's going to be 0, 1, 1, 1, 1, and then we're just going to have 0, 0, 0. Because when we move that 1 over, we're not just moving that, we're multiplying the whole thing by 2 times, which means all of this is going to be moving over as well. And we're going to end up with 2 to the power of 22 as our 22 being our new exponent. To get 22, we're going to still start with 2 to the power of 4. So we'll start at our fifth bit. So 1, 2, 3, 4, 5. So that's still going to be 1. And we can still, well, we can't go, so 16 plus, okay, so we're going to have 1 right here. So 16 plus 4 is going to give us 20, and then 1, and then we'll have 0 right here. And so that's going to be our answer. Let's go ahead and check the answer. And yeah, we are good to go. So now, again, this is a great example of understanding how floating point numbers work. Let's move on. Okay, so in our previous examples, we've mainly looked at how to normalize positive floating point values. So in our last example, we had a mantissa that started with 0. And in the very first example, we also had a mantissa that started with 0. What happens if we have a negative floating point value that we want to normalize? Well, in that case, things are going to get a little weird. So if you look at the mantissa, it can be represented this way: 1.110110 times 2 to the power of 00001010. Now, if we take our exponent and convert it to Denary, we've got 2 to the power of 1, 2 to the power of 3. So we're basically going to have 8 plus 2. So we're going to have 1.110110 times 2 to the power of 10. Now, basically what we want our mantissa to look like at the end of this process is like so. We're going to have 1.0 and then something else. Now, what we're going to have to actually do is make sure that we have a 0 at this spot. And the only 0 we can move there is right here. So we're going to have to move this 2 decimal places over here. So what we'd essentially end up with would be 111.01100 times 2 to the power of 8, because we need to subtract 2 from the exponent to essentially multiply this number by 2 twice. Now, there are a couple of problems with this. First, when representing normalized values in a mantissa, we cannot go beyond the first decimal point, or we can't go beyond the first value on the other side of the decimal point. So that means that we have to get rid of these. So really our answer would be 101100, and then we have 8 bits in our mantissa. So 1, 2, and then that's going to be 8. So we can fill in the other values with, so we're going to have, so if this is 4 or this is 5, so those are going to be our other values. And that's still going to be times 2 to the power of 8. But the thing is, like, we are losing a lot of precision. We're basically getting rid of those 2 values, which means that this value doesn't even really represent what it's supposed to. It's normalized, but we've lost data in normalizing it. And this is one of the reasons why I really haven't seen any negative floating point normalization problems on the A-level exam. Because it's like, it's something that follows the conventions of normalization, but is not really practical in the real world. There's no reason why you'd ever want to do this. But if we were to follow this through, we'd have 0, 1, 1, 0, 0, 0, 0, times 2 to the power of, and for exponent we had 8 bits, so it'd be 0, 0, 0, 0, 0, or actually be 1, 0, 0, 0 for 8. And then we could go ahead and write our answer as 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. And this would end up being our answer right here. Now, I just want to present this for your information, but just know that this probably won't come up on the exam, and it really doesn't make a lot of sense. This is a great example of math that's done on the A-level exam that, like, I guess works in the exam, but doesn't really have any application in the real world. Anyways, that being said, I just wanted to address something that you may have wondered about, and that hopefully gives you a better understanding of normalization and floating point numbers in general. Let's move on. So now that we've basically covered normalization and we've gone through a bunch of examples involving normalization, I want to sort of summarize this topic by giving you some details as laid down in bullet points. So if you have negative floating point numbers, our mantissa starts with 1, 0, and we basically need to alter the mantissa and the exponent in order to reach that particular value. We're not going to add to the exponent. That's something that I will get rid of, but we're still going to be subtracting from the exponent. If we have a positive number, a positive floating point number, we're going to have a mantissa that starts with 0, 1, and we're going to be subtracting from the exponent, which is also what we're going to be doing up here in this case. So in both cases, we're going to be doing that. Now, there are a couple of reasons why we use normalization. So first, it allows us to store the maximum range of numbers in the minimum number of bytes. Particularly if we look at an example of an unnormalized binary value, particularly a positive value. So right here, this was unnormalized. But we had a lot of zeros where we didn't need to have them. So all of these could essentially have been eliminated. And we were able to do that through normalization. We did add some more zeros right here, but if we could only store 4 or 5 bits, that would have been enough. So in cases where we don't have as much storage, this can be very useful. So that's a great example of how we can store the maximum range of number in the minimum number of bytes or bits, and how very large and very small numbers can be stored with accuracy. Because again, if we have a mantissa that looks like this, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1. Now this is like 5 digits. We got 5, got another 5, we got another 4. So that's like 14 bits. And then maybe we have like 8 bits for our exponents. Our exponent is like 0, 0, 0, 1, 0, 0, 0. But if we normalize this, then we can basically get rid of all of these. We can move up the 1 right here. We can get rid of this too, really. And we could just end up with 0, 1, 1. And then instead of 14 bits, we just need, well, I guess it'd be 0, 1, 1. Yeah, instead of 14 bits, we'd really just need 4 bits to store this. And our exponent would probably be the same size, so these would be our exponent bits. But still, we've reduced from 10 bits to 4 bits, which means we were able to store a much bigger number and a smaller amount of memory. So in case you haven't realized, like if you look, for example, at well, actually, let's look at an A-level example, right? Now, right here, we have 8 bits, so 8 binary digits in our mantissa, and we have 8 in our exponent. So actually write these in different color. Now, this is the storage that's allocated to each one of these values in a computer system. So we have a limited amount of space in which we can store these values. Therefore, if we can minimize the amount of space that's taken, then everything becomes much more efficient. We're basically accomplishing the same task with less memory needed. Now, additionally, because we need to use less bits to represent numbers, we can also have a higher precision or accuracy for a given number of bits. So if we can represent a larger number using less bits, then we're more likely to have a situation where we don't need to cut off numbers, or we don't need to sort of get rid of digits in order to make sure that they can be stored in a particular number of bits. So higher precision accuracy represent a greater range of numbers, store very large or very small numbers. We can also avoid the possibility of many numbers having multiple representations. So this kind of goes back to having more accuracy. Anyways, that's the gist of normalization. Let's move on to another concept now that we understand this with, I think, some depth. So now let's take a look at converting from floating point to Denary. So here we've got a mantissa and an exponent. Let's go ahead and let's write these out. So the mantissa is going to look like this: 1.011000111 times 2 to the power of 0001111. Now, nothing has been said as to whether this mantissa is already normalized, so we can just assume that it is. If there are problems where it doesn't say whether it's normalized or not, it's going to be normalized. So let's start by converting this exponent. This exponent is going to be the power of 0 to the power of 1 to the power of 2. So 4 plus 2 plus 1 equals 7. So we'll have 1.011 0001111 times 2 to the power of 7. The thing is, the first thing we want to do is we actually want to eliminate our exponent value. So we want to get rid of this right here. And to do that, we want to end up with 2 to the power of 0. So that means that we're going to move our decimal place. So essentially, we're going to have to make this number right here much, much smaller, or rather much, much bigger. So we want to make that bigger to compensate for our exponent right here being 7 places smaller, or being smaller by 7 times, let's say. So 1, 2, 3, 4, 5, 6, 7. So what we're going to end up with now is going to be 1, 0, 1, 1, 0, 0, 0, 1, 0.11, and that's just it actually. So what we actually want to, so this is going to be our new binary value. And so what we actually want to do is we want to take this and turn this into a Denary value. Now to do that, we're still going to be working within the confines of floating point numbers. So this one right here was -1 in this format, but it's still going to be negative. But we need to look at this in terms of not only floating point numbers, but binary floating point numbers in general. So this -1 turns into -128, and this is going to be so we have -128, 64. So it'll be -128 plus 32 plus 16 plus 1 plus 1/2 plus 1/4 for the decimals. So this first number is still going to be negative, and that's probably the thing that trips people up the most. So we're going to end up with -128 plus 48 plus 1 plus 3/4. So -128 plus 49 plus 3/4. So this is still going to be a negative number. This is going to end up being, so -128 plus 49 ends up being, so let's say, that's going to be 79. 79 plus 49 would give us 128. So -79 rather. But then if we add 3/4, we're going to end up with our answer, which is going to be -78 1/4, or -78.25. And if you check our mark scheme, that is indeed our answer. We would get 1 point for working out the exponent, 1 point for working out the mantissa, along with 1 point for the correct answer. And right here we can see our mantissa, and we have our exponent right here as well, being 7. So let's move on. So now let's take a look at converting from Denary to floating point. So right here in this problem, it says real numbers are stored in a computer system using floating point representation with 10 bits for the mantissa, 6 bits for the exponent. And we don't have to worry too much about 2's complement form, but we need to calculate the normalized floating point representation of negative 7.25. So negative 7.25. Actually, I'm going to switch to 1 right here, or to blue right here. Now the first thing we can do is we can write a 1 here because it's negative. So we've got that. Now the next thing we're going to do is convert this into fractions. So we're kind of going to go backwards in terms of the process that we did in our previous example. So we can say this is negative 7 1/4, which is going to equal negative 29 over 4. And what we're going to need to do is we're going to multiply this fraction by 1/2 multiple times. And it'll kind of make sense as to why we do that as we kind of go along. So we have negative 29 over 4, and we're going to multiply this by 1/2 until our denominator right here is bigger than our numerator. So it's bigger than 29. So this is going to become, so we're going to have negative 29 over 8, negative 29 over 16, negative 29 over 32, and then we're done. And that means that we had to multiply our initial value by 1/2 3 times. And that's going to give us our exponent. So we have 1 multiplied at 1, 2, 3. So our exponent is going to be equal to 3, and we're going to convert that to binary. And that's going to look like this. So 1, 1. Actually, I'll go ahead and 1, 1, 1, 1, 0, 0, 0, 0. So we've got our exponent. And now what we're going to do is we're going to work with this number that we have at the moment. So we've got negative 29 over 32. And we already have a 1 right here. And if that's going to be negative 1, then we want to find what the difference is going to be between both of them. So basically we've got negative 1 plus what is equal to negative 29 over 32. And the answer to that is going to be 3 over 32. So x equals 3 over 32. So this 3 over 32 right here is going to be the rest of our mantissa. So that means that we need to think about how we can represent this in our mantissa using the biggest possible fractions. So this is going to be equal to 1 over 16. And 1 over 16 just represents 2 over 32 plus 1 over 32, which ends up giving us 3 over 32 at the end. So if we take a look at our mantissa and we consider the fact that the first value is just going to be to the power of 0, and next we're going to have 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1, 1/28, 1/56, and 1/512, then we can see what to fill in. We're going to fill in 1 over 16 and 1 over 32. It's going to be 1, 1. And everything else is going to be 0. So we're going to have 0, 0, 0, 0, 0, 0, 0. And this is our answer. So let's go ahead and check the mark scheme. And we are good to go. We got the correct answer. Now, this is really just basically the reverse of what we did when we were converting from our Denary values to our floating point values. Essentially, we're seeing how many times this would be to, our decimal would be to the power of 2, or basically our mantissa would be to the power of 2, using this part right here. We are separating our negative 1 out for our first digit right here. And then whatever is left over is going to become what is in our mantissa. So let's move on to another example. Now right here, this is very similar to our previous problem, but we have negative 202. So here there is no fraction. That's the reason why I wanted to work through this problem. So here we have negative 2 over 2. And we basically need to multiply this by 1/2 again. So if we start out with negative 2 over 2 over 1, we need to multiply this by 1/2 until we have a denominator that's greater than our numerator. One thing we can do before we get started is we can just make this 1 because it's a negative number. But basically, we're going to go to 202 over 2, 202 over 4, 202 over 8. I'm kind of doing this because it's easy to get confused otherwise in this process. 202 over 16, 202 over 32, 202 over 64, 202 over 128, and 202 over 256. So we can go and count these up. This was the first time, and 8. So we multiplied it 8 times. So that means that our exponent is just going to be 8. So 1, and then all of these are going to be 0. Okay, so we've got negative 202 over 256 right here. And so we need to figure out the difference between negative 1. So negative 1 plus x equals negative 202 over 256. That means that x is going to be equal to, okay, so that's going to be like 54 over 256. So if you think in terms of multiples of 2, like 64 is not going to fit, like 64 is going to be too big, so we can't do 64 over 256. But we can do this, we can do 32 over 256. So 54 over 256 is going to be equal to, so the first value, the biggest fraction that's going to fit in, is going to be 32 over 256, which, let's see, that's just going to be 1 over 8. It's 32 over 256. Okay, so we need to work up to 54 over 256. So 1 over 16 is going to be 16 over 256. So I think we can safely add that. Equals 1 over 16. That's going to give us 48 over 256. So we still have 6 over 256 left. 1 over 32 is going to be 8 over 256. But right now we only have a difference. So right now we are at 48 over 256, right? So we need to get a fraction. We need to get fractions that give us 6 more out of 256. And 1 over 32 is 8 over 256. That's too much. So we could probably do 1 over 64, which is going to be, so that's just going to be 4 over 256, which gets us up to 52 over 256. And then we can go up to 128, 1 over 128, which gives us 2 over 256, which gets us to the finish line, so 54 over 256. Now we can go ahead and fill in the rest of the mantissa with these values. So if we just go ahead and do 1/2, 1/4, 1/8, 1/16, 1/32, 164, 128, then we have just enough space with just enough bits. And so we're going to fill in 1 right here, 1 right here, 0 right here, 1 right here, and 1 right here, and 1 everywhere else. And that's going to be our answer. So let's go ahead and let's see whether that was correct or not. And yeah, we are good to go. Now our final example of converting from floating point, or converting from floating point to denary, is going to involve a positive number, which we haven't done before. So here we've got 12 bits for the mantissa and 4 bits for the exponent, and we want to convert the number 65.25, which basically equals 65 and 1/4. And we know this is a positive number, so we can put in 0 right here. And we're going to convert this to a fraction. So this is going to end up being, I'll multiply this by 4, 240. Okay, so this is going to be 260 over 4. Or sorry, 261 over 4. So yeah, 4 times 65 is going to be 260, plus 1 is going to be 261 over 4. So we're going to have to keep multiplying this until until the denominator really is greater than 261, which means we're going to end up with actually 512. So let's see how many times that takes. Okay, cool. So that took 1, 2, 3, 4, 5, 6, 7 times to get there. All right, cool. So just need to make sure I got the math right because I'm absolutely terrible at math. 4 times 65 is going to be equal to, yeah, 240, it's 20, 260. Okay, cool. All right. So we got 261 over 512. And the thing is, right here, we have no -1, so we can just go ahead and just skip that step right there. But we need to figure out what fractions will give us 261. Will give us 261 over 512. And actually, before we do that, let's fill in our exponent. Our exponent is going to be 7. So that means we're going to have just 1, 1, and 1. Okay, so we already have the first digit of our mantissa, and now 261 over 512 is going to be equal to, so I think we can actually just say 1/2 right off the bat, because 1/2 is equal to 256 over 512. And then we're going to need something small, so we're going to need 4 over 512, which is going to be, so 4 over 512 is going to be 128. Let's see, 4 over 512, yeah. 2 over 512 would be 1 over 256, so 4 over 512 is going to be 1 over 128. So we can do plus 4 over 512. And that puts us up to 260 over 512, which means that we just need to have 1 over 512 right now. So 1/2, we're just going to write this out. And I know this seems tedious, but I still do this because it's really easy to get confused here. But if I write it out, then everything is absolutely clear. And that's about all we need, because we're only going to 512. So we'll go ahead and fill this in. And we've got 1 right here, 1 at 1 over 28, and 1 at 1 over 512. Everything else is going to be 0. So you can see that's significantly less time consuming than working with negative floating point numbers. Let's check the mark scheme. And yeah, we are good to go. So to kind of give you a summary of all of the steps involved, I created a list right here. I'm not going to go over it, but this is something like this. There's going to be a link to the slideshow in the description, and this is something you can look at to kind of give you a clear representation of how to go about converting numbers from floating point to Denary, or rather from Denary to floating point. So now that we've covered the other types of conversions, let's go over how to convert from binary to floating point. So here's another A-level problem. And right here it says numbers are stored in a computer using floating point representation with 12 bits for the mantissa and 4 bits for the exponent. Write the normalized floating point representation of the following unsigned binary number. So if it's unsigned, we're going to assume it's positive. And we want it to be normalized. So that means that our mantissa is going to look like this, 0, 1. Now in order to take this and achieve that, what we can do is we can simply move our decimal point up. So we can say 1, 2, 3, 4, 5, 6, 7. So let's go ahead and draw that again. There we go. Okay. So we're moving it up 7 places, which means that our new value is going to be, we're going to have 0.1, 0, 1, 1, 1, 0. Then we've got 3 zeros. And 1, 1, 0, 0, 1. And so if we remove our little decimal point, that's going to be our mantissa. But the problem with this is that we only have 12 bits. So let's go ahead and count and see how many. Well, so if actually, first of all, before we move on to that, our answer would be this times 2 to the power of 7, because we moved up 7 decimal places. So that means our exponent is going to look like this. But if we just look at our mantissa, as we said, our mantissa is just going to be 0, 1. This is going to be the same thing without the decimal point. But we only have 12 bits in which to represent this value. So let's actually see how many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that takes us up to 12 bits. So that means that we're actually going to have to get rid of the last 2. So these are going to be gone. And this is an example of overflow where we need more bits to represent a value than we have. Overflow. And that's because this number it's not necessarily that it's too big, but there's maybe too many decimal places. Well, really just too many digits in general. So we're going to lose some precision, but we can still represent the value this way by cutting out the last two digits. So we're going to end up with an answer of 0, 1, 1, 1, 0, 0, 0, 1, 1, 0. Let's check the mark scheme to confirm. And yeah, we are good to go. 0, 1, 0, 1, 1, 1. Okay, cool. And so that's actually pretty straightforward. That's how you deal with a problem like that. And so right here, it's to state the consequence of storing the binary number in part A as a floating point number in the system. So the consequence is really going to be loss of precision because we had to cut off a few decimal points. And the reason for that is going to be because of the fact that we needed 14 bits to represent, but we only have 12 bits. Only 12 bits are available. And as a result, we had to truncate or get rid of the least significant bits of the original number, which were just those digits at the end, which we represent in yellow right here. So now that we've come across the concept of overflow, let's talk in theoretical terms about what that actually means. So overflow is when we get a number larger than the maximum value that can be represented in the given floating point number. And overflow occurs when a calculation produces a number close to 0. So it's really too small to be represented using the number of bits that we have. It's essentially the same concept, both overflow and underflow. Basically, we have a number that we can't represent in the number of bits that we've been given. And the result is usually going to be loss of precision because we can't store all the values necessary to describe the quantity that we want to represent in the most accurate way possible. And that often results in us cutting off the least significant bits. That means that those bits that are going to be on the furthest right of the value. So if we go back to our example right here, again, these were the least significant bits that we cut off. Anyways, that is essentially what overflow and underflow is. You are largely not going to have to use that term, but you do need to be able to explain, as we did in this question, like when and why you had to cut off a part of a number to fit into a mantissa, or to fit into the space allocated for a mantissa in a given computer system. Okay, so now that we have a more solid understanding of the concept of overflow and underflow, I want to go over one last example problem before we wrap this up to really hammer home this concept. So right here it says we have system 1, which uses 10 bits for the mantissa and 6 bits for its exponent. And we have system 2, which is 8 bits for the mantissa and 8 bits for the exponent. Calculate the normalized floating point representation of 113.75 and show how to be represented in each of these systems. So we're going to go ahead and convert 113.75 to a floating point number. And we're going to turn this into a fraction, so 113 3/4. And if we go ahead and turn this into an improper fraction, that means we're going to end up with, say it's going to be 400. And so we're going to have 452 plus 3, so 455 over 4. So we need to go through that whole process. So we have 455 over 4, 455 over 8, 455 over 16, over 32, and we're at 455 over 512 because remember our denominator needs to be greater than our numerator. So if we count all of these up, we've got 1, 6, and 7. So we can go ahead and fill in our exponent because those are going to be the same for both of these. So our exponents can be 7, which in binary would just look like this. And if we wanted to show this in our system 2, we're going to have the same answer, but because we have more bits, we're just going to have more zeros. So it would just look like this. Not a huge difference there. But now that we have this fraction right here, we want to turn this into, we want to find out what our mantissa is going to be. So this is going to be a little bit complicated, but we can start with 1/2, because 1/2 is going to be 256 over 512. And that's going to leave us with, actually, okay, so that's going to leave us with about 199 over 512. And I think it's safe to say we can add 1/4, And 1/4 is just 1/28 over 5/12. And so that means now we're going to end up with 71 over 5/12. So that's what we have left that we need to account for. Yeah, 71. Okay, that makes sense. Now next, let's see, we have 1/8. 1/8 is going to be 64 over 5/12. So we can go ahead and do 1/8. 64 over 5/12. And remember, these all need to add up to 455 over 5/12. And so if we have 64 over 5/12, we still have 7 over 5/12 that we need to account for. So probably the next fraction we're going to want is going to be 4 over 5/12, which is going to be 1 over 128. It's going to be 1 over 128. And yes, that's just going to be 4 over 5/12. So we still have, so that means we still got 3 over 5/12 to account for. And then we're going to add up, okay, so we're going to need, 1 over 256 and 1 over 5/12. 1 over 256 is going to be 2 over 5/12. And then 1 over 5/12 is just going to be 1 over 5/12, which accounts for this 3 over 5/12 that's left over right here. So let's go ahead and let's write out our fractions in our mantissa. So if you look at our mantissa, the first digit in both is going to be 0 because this is a positive number right here. So we're going to have 0 and we're going to have 0 right here. Now we'll start with this one right here, 1/2, 1/4, 1/8. And again, I'm writing out these fractions because otherwise it's just really easy to make a mistake here. 64, 1 over 128, 1 over 256, 1 over 5/12. And to be clear, this is the mantissa with 10 bits, so we can represent 10 digits. And we have just enough bits to represent all the fractions that make up 455 over 5/12. So we're going to put a 1 here for 1/2, 1 for 1/4, 1 for 1/8. And then our next one is going to be at 128, 1 over 256, and 1 over 5/12. So you have 0, 0, 0. But unfortunately in system 2, we only have 8 bits. So we can't really represent this entire mantissa. So we're going to have to cut off the last 2 digits, which are going to be these right here. So that means we're just going to be stuck with 1, 1, 1, 0, 0, 0, 1. And we're simply going to leave off the last 2 because here we have a case of overflow. And that's another great example of how this concept works. Now, I'm just going to close out this video with a couple of channel updates. So I'm planning on taking a 1 to 2 month break, during which I'm going to dramatically slow down the pace at which I'm putting out videos. I'll be working on an online course that focuses on Java for paper 4 during that time. And I've decided not to create a machine learning course just because I don't think there's a lot of demand from particularly A-level or even IB students for this type of course. And during that time as well, I will be working on topic 20, which is a very large topic, and I do hope to put out some videos. But like I said, probably the only thing I'm going to be putting out will be a topic 20 video, and the rest of my time is going to be devoted to creating my online course. Anyways, I hope this video was of value to you. If it was, please consider subscribing to the channel and give the video a like. Have a nice day.